This video is going to show you how to use the energy calculation at National 5 level. It can start out quite basic, where we are just multiplying out three values, but sometimes you are asked to rearrange an equation. So relating this back to the experiment that would have went alongside it, you would normally calculate the energy absorbed by a substance. In class you would normally use water. So if we take this diagram, you would burn some sort of fuel, maybe ethanol or methanol, in a spirit burner. That's represented by the green liquid. When you burn that, it will release energy, and majority of it should pass through that copper can, maybe absorbed by the can, but pass through hopefully and go into the water. Now obviously there's a lot of issues there where the diagram shows no draft shields, so a lot of the heat is going to be lost to the surroundings. The can will absorb it. You would want to stir that water, some of the heat could go out the top, so lots of issues, but it should give you a rough idea how much energy was released by the fuel by working out what that water absorbed. And if you understand the principle of that, it can make the calculation make more sense. So this is all dependent on what is in the can. So if it was water, you would want to work out the energy absorbed by the water by doing E equals Cm delta T. So three parts there on the right. C is specific heat capacity. Now for water, this value is in the data book and it's always 4.18. If the can does not contain water, you will either be told the specific heat capacity or you will be asked to calculate it. M is the mass of the substance in the can, so what's been heated. Be careful, sometimes you will be given a few mass values. Normally they give you a value for the mass of the fuel. Don't need that, it is just what's in that can. And then delta T as well, that is the temperature change of what's in the can. So say the water started at 20 degrees, went up to 40, that change would be 20. So few wee points I've added in is all the units. Make sure you're aware of those. The specific heat capacity one is in the data book. The rest you'll just need to be aware of. For mass, normally you'll be given it in grams or as a volume in cubic centimetres. So just be aware of that conversion. And also delta T, as you do the rearranging questions, the more complex ones in past papers, you'll need to be aware that you always do the final temperature, take away the initial temperature to get the difference, or the bigger number minus the wee number. So we'll go on to looking at a simple question and then move on to the harder ones. I'll keep referring to this diagram to help make a wee bit of sense of it. So here's one question where it says when 5 grams of ethanol was burned, so going back to this here, you have 5 grams being burned. You have 200 cubic centimetres of water in the can, and that water was increased from 18 degrees to 32 degrees. Calculate the energy absorbed by the water. So what we're going to do for E equals Cm delta T, you want to rewrite that. You can either do it in two ways. Some people like a wee extra step just to see what's going on, and we'll apply a colour to each one. So E is going to be the energy, and it does say calculate the energy absorbed. It might say released, but it will be the same value. So E is what we want, so a question mark. C is always given, and it isn't in the question because it's water, and it's expecting you to know that water is 4.18. M is the mass of the substance heated, so it's the mass of the water. So take careful, there's a prime example of a common mistake. Some people would choose 5, others would choose 200. Now again, we're not using that number directly, because we said on the initial thing that it had to be in kilograms. To get into cubic centimetres to kilograms, we have to divide by 1000. So that would become 0.2 kilograms. Now delta T is always final temperature, T2, take away the initial. And in that case, you have been given the numbers 32 and 18. So that's 32 take away 18, which will give you 14 degrees Celsius. Okay, so now that you have 3 out of the 4 numbers, you are wanting to do your sum, so either down the bottom side, won't matter. EH equals Cm delta T. EH we want to know, so you want to rewrite it. C is 4.18. M is the mass of the water, is 0.2, and delta T is 14. So you can see some people would skip straight to this section if they're confident with the numbers, but this is an easy question. Later on it can be quite hard to do that. So if you multiply all that out, you should get 11.704 kilojoules. There is a mark for units if the units aren't given, so make sure you do them. Do not round too much, so don't round that to 12 kilojoules. Just leave it as the number in the calculator. So that's an easy one. Going on to a wee bit harder. So using the information from the table, calculate the specific heat capacity of sodium chloride solution. So this is more like an experiment you would see, where you have a table of data. In your diagram, we would have the sodium chloride solution being in the can this time. Doesn't tell you what fuel, doesn't matter. But you're working out what energy has been, well, you're being told the energy absorbed by the solution in the can. You have a mass of what's in the can, and you have the temperature values too. So if we write out the 4 things we need and try and pull them from the question, you will see it says energy absorbed is 38.9. You'll then see that C is what you're asked about. So you have to calculate the specific heat capacity. So C's getting a question mark. M is the mass of the substance heated. We said the sodium chloride is in the can, so you should take the 500. It's in grams, so you want to divide that by 1000 to get it into kilograms. And finally, delta T. You've been given a start and a final. So you're doing T2 take away T1, which is 43 take away 26, which will give you 17 degrees Celsius. So if you multiply this all out and rearrange, so it depends how confident you are. I like to just put in the numbers I have and then deal with them after. So energy is 38.9. C is what I want, so rewrite. M is 0.5. Delta T is 17. So we want C, and it's not on its own like the energy was up here. You're going to have to fix that. So I do that in 2 lines. What I would do first is multiply any numbers out that you can and then divide. So this number can't be multiplied by anything because there's only one. C won't multiply because it's a letter. But if you do 0.5 times 17, you will get 8.5. Then what you can do is for each side, you want to get rid of that 8.5. So to do that, you're going to need to divide both sides by 8.5, not just the one. So if you do that, you will get 4.58 equals C. Now in this question, just because I've went with it, there's no units given for specific heat capacity. It would be the same units as you would normally be given in the data book. So always put in units. So I'll even rewrite that. C equals 4.58 kilojoules per kilogram per degree Celsius. And we're done there. Final one is the hardest of them all, but once you can see the rearranging, this shouldn't be too hard to jump to the last step. So this time we're looking at the final temperature of hot chocolate. So we have a fuel burning and hot chocolate is in the can this time. So writing out your 4 things. We'll go with the same. So energy, it says the energy absorbed is 72.83. Then the value for C, specific heat capacity, is hot chocolate, so we're not using water's value. It says here 3.93. The value for M is the mass of the substance in the can, so it gives you a volume in cubic centimetres, so you can convert that into kilograms by dividing by 1,000. That's 400. Now delta T is an awkward one because we know that delta T is T2 minus T1. We have an initial temperature, meaning we have T1. We don't have T2. So T2 minus 5, we don't know what that value is going to be yet. That's what you're trying to figure out in this question. So you'll see, yes, I'll highlight delta T. Actually, my final answer is what's been asked. Calculate the final temperature, which is your value for T2. So you'll see there will be a wee extra step involved. So what we're going to do here is still do what we can. So E is 72.83, C is 3.93, M is 0.4. We don't know delta T, so we'll put delta T. Just ignoring that 5 just now. So the next line, if you multiply out any numbers you can, so 72.83, there's no number over there. 3.93 times 0.4 is 1.572 times delta T. If we divide both sides by the same value to get rid of one of them, so we're going to divide both sides by 1.572, and that will give you 46.3 equals delta T. Now that's not your final answer, because your final answer needs to be what is the final temperature. So going back up to this line here, because you've now figured out delta T. So we know that delta T equals T2 take away T1. We know that delta T is 46.3. T2 is what we want. T1 is 5 initial temperature. So to get rid of the 5, add 5 to both sides and you will get 51.3 is T2. And that's your final temperature.